Hi everyone. This is a look at a multi-step thermochemistry problem that I call Hess's Law to delta H to H back to delta H. This is a multi-step problem where we're first going to use Hess's Law. We're going to use a balanced chemical equation, use our table of molar enthalpies of formation in the data book, and find delta H using Hess's Law. We're then going to convert that delta H into H by dividing by the moles, only we're going to use a coefficient for the moles. We're going to use the balancing number in the chemical equation of the chemical that the question asks us to focus on. Then, finally, we're going to convert that molar enthalpy back into delta H by this time using mass over molar mass for our moles. Here we go. Calculate the amount of energy released when 25.0 grams of propane burns. Our first step is to do Hess's Law to find that delta H. In order to do that, what we need is a balanced chemical reaction. This is going to be propane burning. It's the hydrocarbon combustion for propane. You might need to double check in your data booklet some of the chemical formulas. You might have to look up the formula for propane itself. It might take a second to balance the reaction. I'm going to dive right in. Propane is C3H8. It's a gas. It's going to react with 5 moles of oxygen gas to produce 3 moles of carbon dioxide gas and 4 moles of water vapor. We're about to do Hess's Law. To do that, we need a balanced chemical reaction. There we have it. Hess's Law itself is going to be the sum of the moles times the molar enthalpies of formation of the products, subtract the sum of the moles times the molar enthalpies of formation of the reactants. Here we go. We're going to start with the products. I'm going to leave the units out in order to make it just a little bit tighter presentation. We have 3 moles of carbon dioxide. So that's 3. Go to the data booklet and look up the molar enthalpy of formation for carbon dioxide. It's negative 393.5 kilojoules per mole. We also have 4 moles of water vapor. That's significant. In the data booklet, water is in here twice. There's a number for liquid water and a number for water vapor. This one's water vapor, which is negative 241.8. Negative 241.8. Again, that's kilojoules per mole, which I'm omitting. That's the product side of the equation. And now we're going to subtract, big subtract right there, the reactants. We have 1 mole of propane. 1 mole of propane. I look up propane in the data booklet. Negative 103.8. Negative 103.8. Again, that's kilojoules per mole. We have also 5 moles of oxygen. Oxygen is not in the data booklet. It's an element. Elements do not have molar enthalpies of formation. That's 0. We have a pretty big calculation to do. Okay, let's type it. 3 times negative 393.5 plus 4 times negative 241.8 minus 1 time negative 103.8. And I got negative 2043.9 kilojoules. That was our first step in this multi-step equation. We did Hess's law to find the delta H of this balanced chemical reaction, and we have negative 2043.9 kilojoules. Our next step is to convert that delta H into a molar enthalpy. We're going to divide by a coefficient, the balancing number of the chemical the question is about. And this question, is very obviously about propane. Okay? So H is delta H over N. The delta H we just found in our question by doing Hess's law. That's negative 2043.9 kilojoules. We're going to divide by the coefficient of propane. Now here the propane is balanced with a 1. Now that's a very uninspiring mathematical move, dividing by 1. However, conceptually, it's very important because the units changed from kilojoules to kilojoules per mole, and what that value represents also changed. We had the enthalpy change, and we converted it into the molar enthalpy. So dividing by 1 here, in this particular example, is not amazing. But conceptually, like I just said, it's very important. Okay? So we found delta H using Hess's law, we converted it into a molar enthalpy, and we're going to go back to delta H, the total amount of energy released. But this time, we're going to use mass over molar mass. These 25 grams of propane are significant now. Delta H is NH. But as we were just saying, we're going to use the mass over the molar mass. So that's going to be mass over molar mass, H. We have 25.0 grams of propane. We're going to divide by the molar mass, again, of propane. Here's the formula, C3H8. We can take our time to find the molar mass. That's 3 carbons, 12.01 each, and 8 hydrogens at 1.01 each. Sorry, I hit a wrong button. The total molar mass is 44.11 grams per mole. The H, the molar enthalpy, is our answer up here. Negative 2043.9 kilojoules per mole. So we have 25 grams divided by 44.11 times negative 2043.9. We got negative 1158.410791. We got a raw answer of just over 1100. To wrap up this question, let's go back to the wording of the problem itself. There's only one number, 25.0 grams. That's 3 significant digits. So here we need our 3 significant digits. Here, we're compelled to go to scientific notation. So it's going to be negative 1.16 times 10 to the power of 3 kilojoules. There is a style of multi-step question that I myself call Hess's law to delta H, to H, back to delta H. That's many steps. First, maybe a question is kind to us and provides the balanced equation for us. However, like this one, we have the ability to figure out the equation all on our own. Then, we do Hess's law to find the delta H. Our second step is to turn that delta H into a molar enthalpy by dividing by the coefficient of the chemical that matters to us in the question. It's not uncommon for us to have to divide by 1. That doesn't change the number itself, but it changes the units and changes delta H into H. Our final step is to convert that molar enthalpy back to a delta H by doing moles times the molar enthalpy, only this time through, we'll use mass over molar mass for the moles. Watch those signs, watch those significant digits and your units. We can get there. And I hope that helps.